Hello Math 4411 students. Let's begin Lesson 10, Homomorphisms and Factor Groups 2. As the title suggests, this is a continuation from Lesson 9. So before starting Lesson 10 materials, let's have a brief recap on Lesson 9 contents, and let's discuss how Lesson 9 topics are associated to Lesson 10 topics, along with a brief overview, basic overview on Lesson 10. Looks like that's a lot. So looks like we'll have to do that for entire video. Okay, let's begin. In Lesson 9, we started with homomorphism. It's a map from a group G to another group G prime that preserves the group operation. Phi of AB is phi of A times phi of B. Here, A times B is a group operation in G, and phi of A times phi of B is a group operation in G prime. So we have two different group operations, yes, in two different groups, G and G prime, but they're connected by homomorphism. So homomorphism preserves all that structure. Now it turns out the homomorphisms preserve not just group operations, but some other things as well. The identity, and also inverse. E goes to E prime as the elements of G goes to elements of G prime, and X inverse goes to phi of X inverse. So basically X inverse is going to Y inverse if Y is phi of X. Is that all? Actually more. It turns out it preserves the entire subgroup structure. You see, group operation is preserved, and we can prove that the identity is preserved, inverse is preserved, and also the closeness is preserved, so entire subgroup structure is preserved. If H is a subgroup of G, then the image under the homomorphism, phi of H, is also a subgroup of this time G prime. But what's most striking is it goes backward as well. If H prime is a subgroup of G prime, then its preimage is also a subgroup of G. So the homomorphism preserves the entire subgroup structure, not only forward, but also backward as well. And is that all? As a matter of fact, there's still one more. It preserves the normal structure as well, the normality. If N is a normal subgroup of G, then phi of N is a normal subgroup of phi of G. And if N prime is a normal subgroup of phi of G, then its preimage is a normal subgroup of G. So normality is also preserved. But here, things are a little bit tougher because we are not considering entire G prime, you see. The target can be too big. So N is a subgroup of G. Doesn't mean phi of N is a subgroup of G prime. G prime can be too big. It's a subgroup of phi of G. Only that much. And if N prime is a subgroup of phi of G, then its preimage is a subgroup of G. So we consider only between blue and green, G to phi of G. G prime can be too big. Of course, if N prime is a normal subgroup of G prime, then it is a normal subgroup of phi of G as well, so everything works out. But this direction, it may not work because G prime is bigger, you see. Remember the property of the normality? Let's see. Yeah, basically the conjugation belongs to the candidate or not, that's the key. And then we have to consider that for every element of the group. But if you consider a bigger group, then we have to consider more candidates of G's. So there is more chance things can go wrong. So if you take bigger group, then the same subgroup may not be normal subgroup of bigger group. For smaller group, yes, because there are less number to take. So if n is a subgroup of G, let's see, if n is a normal subgroup of G, then, and if there's any subgroup in between n and G, then yes, it's normal. But if you take bigger group, G prime, then it may not be normal there. So we went through various properties that are preserved under homomorphism. Homomorphisms preserves the algebraic operation, the group operation, that was the definition. But from there, we could prove various things. The identity is preserved, the inverse is preserved, closeness is preserved, and that's a bit too trivial, but associativity is also preserved. Subgroup structure is preserved, both forward and backward. And also, normality is also preserved, but it comes with a bit of a glitch. Looks like we covered a lot of things, but still a couple more to talk about. The kernel of a homomorphism is defined like this: the preimage of the trivial subgroup. So it's a preimage of a subgroup. So this is subgroup 2. But it has some special property. Number 1, the homomorphism is one-to-one if and only if the kernel is trivial, just E alone and nothing else. Number 2, kernels satisfy this interesting property. The left coset and right coset are the same. In other words, the kernels are all normal. And speaking about normal, yes, all kernels are normal, but maybe not necessarily the other way around. Or is it? That's something we're going to discuss later. Anyway, if the left coset and right coset are the same, then we call such subgroup the normal subgroup. And we have various properties associated to those. And we have more practical criteria which revolve around the conjugation. And the way the normal concept is connected to what we are going to do in lesson 10 is through the normal equivalence. Please recall that the left coset relation and right coset relation are both equivalence conditions. Equivalence relations, as we proved in lesson 6, I think, when we learned cosets and Lagrange theorem. And cosets were equivalence classes of those left coset relations and right coset relations, remember? But for normal subgroups, left coset and right coset are the same, so we do not have to consider left coset and right coset in left coset relation and right coset relations separately. Just throw this away and let's consider this only. And instead of calling it a left coset relation, we'll just call it the normal equivalence relation. More precisely speaking, the normal equivalence relation modulo n, because everything began from a normal subgroup n. Now that we have the equivalence relation, we can consider equivalence classes and the set of all equivalence classes, which we call the quotient set. Now in this quotient set, in other words, the set of all equivalence classes, in this case set of all cosets, we can induce an algebraic operation like this. Xn times yn is x times yn, and this x times y is a group operation in G. So this operation here, if it is well defined, is an induced operation induced from G. But whether it is well defined or not is a big deal. We have a problem because this xn is not unique. This yn is not unique. We may have a little bit different we may have different representatives, basically. So we may end up with this kind of situation. X1n is equal to X2n, and Y1n is equal to Y2n, yet X1n times Y1n is supposed to be defined as X1 Y1n. But what if this is different from X2 Y2n, which is X2n times Y2n? What if we have something like this? This here, blue, and this here, blue, are the same. This here, green, and then this here, green, are the same. So we have to have the same conclusion if this is well defined. But what if this one here, purple, and this one here, brown, are different? Then everything breaks down. We have to prove that this never happens in order to satisfy this. And then based upon that, we have to prove that we have a group structure under this induced operation. We need a lot of steps. But assuming we accomplish everything, we have a new group, which we call the factor group. And that's the topic for lesson 10. Factor groups, and then the fundamental homomorphism theorem is, as a matter of fact, homomorphism between the factor group and the original group, as a matter of fact. And then some factor group computation, some further things about normality. They're all revolving around this. But of course, doing everything all at once is going to be a bit too difficult. So we're going to divide those and take some baby steps here and baby steps there. And I'm not exactly sure whether taking too many baby steps are actually a good thing or not, because we may end up taking too much detour. So I'll consider both options: straight ahead way and then baby steps way. Long way around, but each individual steps are easier. Difficult path, but direct path. Consider both and you choose. There are a lot of things to do, and many of them have to become optional videos, I think, because they can be pretty deep. Anyway, that's what we are going to do in lesson 10. So that concludes the recap and the connection and overview. And from the next video, we're going to start new topics from section 4 and on.